Vectors can look incredibly abstract the first time you see them. It often feels like you're trying to read a foreign language, made up of weird brackets and floating numbers. But by the end of this video, we are going to decode that language completely. We'll start by understanding exactly how vectors describe physical movement, and then use that logic to solve complex, multivariable algebraic equations. To get the most out of this, you only need two things: a basic understanding of x and y coordinates, and the ability to solve simple linear equations. Mastering vectors provides a universal mathematical tool to describe physical space, and a reliable method to secure high-value marks on your Edexcel exams. At its core, a vector is simply a highly precise set of travel instructions from one point to another. It represents the journey itself, regardless of where that journey actually starts. This 2D grid shows a diagonal arrow connecting 2 points. That arrow is our vector. We measure its path by breaking it into exact horizontal and vertical distances. We record these specific steps using column vector notation, tall brackets holding a top and bottom number. The anatomy here is strict. The top number dictates your movement left or right. The bottom number dictates your movement up or down. A positive top number means move right, and a positive bottom number means move up. Warning tone. A common mistake beginners make is reading this notation like a fraction. Notice that there is no dividing line between these two numbers. They are entirely separate instructions. Think of a column vector as a coded map. It perfectly translates a physical, geometric path into stacked numbers for algebraic calculation. Once we have these stacked numbers, we can perform mathematical operations on them. Vector addition is just combining two separate journeys to create a single, uninterrupted path to a new destination. This diagram shows how we add two vectors. The rule is simple. Top numbers are added exclusively to top numbers, and bottom numbers added to bottom numbers. Vector subtraction follows this exact same isolated logic, simply subtracting the second vector's numbers from the first. You will also encounter what we call a scalar. A scalar is simply a regular number that sits outside the vector. It changes the size or scale of a vector, but it has no directional power of its own. This diagram shows a single scalar number positioned outside our bracket. To apply it, the scalar must multiply both the top horizontal component and the bottom vertical component, resulting in a newly scaled vector. Whether adding, subtracting, or scaling, the foundational law remains exactly the same. Horizontal and vertical dimensions never interact. They run on independent parallel tracks. Let's look at this animated diagram. It displays a classic multi-step Edexcel exam question. We have a scalar, vector addition, and unknown variables x and y that require algebraic isolation. To solve this, we enforce the order of operations. First, distribute the scalar 2 into the first vector, making it 2x and 6. Next, add the left side vectors into one single bracket. The top becomes 2x plus 4. The bottom is 6 plus y. Because the vectors are equal, the left components must equal the right. We pull out the top row. 2x plus 4 equals 10, which solves to x equals 3. The bottom row, 6 plus y equals 11, revealing y equals 5. Complex vector problems become straightforward when you use the order of operations to strip the notation down into basic, solvable algebra. You just translated a highly abstract concept into a perfectly solved multivariable exam problem. Any column vector problem you face in the future can be completely dismantled using this exact method of isolating horizontal and vertical components. To solidify your muscle memory, you should immediately apply these proven principles to other past paper questions. Vectors are no longer an obstacle. They are a mastered tool in your toolkit.